smaller and faster memories as compared to a single storehouse. Now, the cache and main memory, since they were volatile in nature, we needed a secondary memory which could store all the instructions, programs, data, processes, softwares, their backups, everything. And then whenever we have to run a process, obviously it should be run on a faster, which is a smaller memory right now. So what we do is we take a backup or a secondary memory called as virtual memory. And then we discussed that when we talk about hierarchy, in the first hierarchy comes your, I'll just take the marker, just a minute. Yes. So in the first hierarchy comes your cache, the fastest, followed by main memory, followed by magnetic disks, then magnetic tapes. And when we talk about the secondary storage, which is your secondary memory, or the hard disk also sometimes, this is subdivided into lots of processes, right? Every process will have its own set of series of instructions and data which will be stored there as one process. Then in order to collocate certain processes, we divide the entire secondary memory into smaller subparts. What are these parts called? Am I audible?
Yes, ma'am, you're audible.
फास्ट तो नहीं हो रहा है? लास्ट टाइम थोड़ा बता दिया था, कोऑर्डिनेशन से नहीं बन रही थी इसलिए थोड़ा सा ब्रश अप करा रही हूँ. So what are the smaller parts in the virtual memory called?
Pages,
Yeah.
frames, or
Yes. So pages. So one process can have n number of pages depending upon the process size, right? And then we can have multiple processes and certain pages associated with each process. Then, um, since your secondary memory or the virtual memory was the backup or the main storage source for all instruction and data, then and when power was switched from off to the on state, the volatile memories cache and main memory were empty. So any address that will come from the processor will definitely suffer a cache miss also and a page miss also. So a page hit and a page fault from the main memory can take place, which results in passing on the address to the virtual memory. Obviously, virtual memory, since it is the main backup, excuse me, yeah, so since it is the main backup, uh, definitely the process would be found there. And then the entire process is not shifted to the main memory. It is only a part of the process, which is a few pages, which are shifted from the virtual memory to the main memory, right? So this relocation takes place, and this relocation is mapped into a table called as a page table. So I was telling about the page table last time. आप लोगों को समझ नहीं आ रहा था, so I brought these diagrams. Now, uh, yes, so a few pages are being transferred from your virtual memory to the main memory, and then definitely a few blocks of the page, respective page, from the main memory to the cache as well, right? Can you just hold on for a minute? Yeah. Yeah, I'm sorry, there was some problem. Yeah. So let's get back. We were discussing about Yeah, so the main process which is in the virtual memory, which the processor is looking for and which wants to run, will definitely be run on the main memory. And then a subcopy of, yes, I was telling you about pages and blocks. So your virtual memory has subparts called pages. The page size in a virtual memory and in the main memory remains the same. Fine. So main memory, though being smaller in size, will have pages which are of the same size as that of the virtual memory pages. Getting?
Yes, ma'am.
All
Ma'am,
right.
but I had a confusion. Are not there frames in the main memory?
See, we call these as frames as well as pages. So there is no problem about the terminology. I guess I told you this
Okay.
thing last time. That
Yeah, yeah.
in fact,
Yeah,
I flash also. So you can call them as a page as well as a frame. So it hardly does matter.
yeah.
But the only thing which matters is that the size of one subunit in the secondary memory and one subunit in the main memory remains the same. Fine. So somewhere in literature you will find the term as a frame. Somewhere you will find it as a page. Um, somewhere I think in your book also it's mentioned as a page, but I have read about frames as well in some literature. So it is called as frames also. There is no problem about the terminology. Okay. Now, since your page or the frame is larger in size, this will have some smaller subunits, and each smaller subunit is a block. Fine. A block size in the main memory and that in the cache remains the same. I hope that's clear.
Yes, ma'am.
या एंड इसके ऊपर बेस्ड हम न्यूमेरिकल्स भी कर चुके हैं अब तक काफ़ी सारे वी हैव डन ट्यूटोरियल शीट्स ऑल्सो एंड उसमें भी काफ़ी सारे न्यूमेरिकल्स हैं विच आर डेजिग्नेटिंग यू द पॉइंट दैट द ब्लॉक साइज इन मेन मेमोरी एंड दैट इन द कैश रिमेन्स द सेम राइट so I will just revise it in a second. Your secondary memory, which is the virtual memory, has main processes which are stored, right? uh, it has sub blocks called pages. We can call them as frames as well. These pages, a few pages will correspond to a specific process. When the power is switched from off to the on state, the address will be a virtual address, right? There is an address mapping that takes place. We'll discuss it later. And then, because there's a cache miss, there is a main memory miss, the address goes to the virtual memory. It fetches the respective process from there, creates a subcopy of the process on the main memory since it is faster and we don't want to miss anymore. So this process starts running here with respect to a few pages which are brought from the secondary memory to the main memory, right? The page size in the main memory or the frame size in the main memory and the secondary memory remains the same. If we are talking about paged memory virtual one, if it is a segmented memory, then the case is different. So we discussed this concept also about segmentation and pages. Right now we'll just talk about pages, okay? आ रहा है समझ आ रहा है सबको?
Yes, ma'am.
Right. So, and these pages definitely which correspond to a specific process are automatically updated because as and when they are needed, right? And then since we want the process to be more faster, a sub block from the respective page is brought and kept into the cache, and this all depends upon locality. And what is the locality? We can either have a spatial locality or we can have a temporal locality. A spatial locality says what?
Like the memory which is the nearest
Yeah.
should be accessed more.
Absolutely. So this means if I'm talking about a process, I will just draw it for you. So if I have a process, which occupies this much of the memory space, definitely in terms of space, they're all co-located, no? आसपास ही located हैं. They're located nearby with respect to each other. And once you are picking up data and instructions of the respective process and bringing it into the main memory, this is based upon spatial locality now. तो जो पास पास पड़े हैं उनको उठा मतलब एक ही प्रोसेस की बार बार जरूरत पड़ेगी ना यू गेटिंग so
Yes, ma'am.
with respect to one process we will have say 1,000 instructions for example 1,000 codes which are written 1,000 lines of code. Now this 1,000 line of code obviously is written together ना ऐसा तो नहीं कि एक इंस्ट्रक्शन एक लोकेशन पे है दूसरी 10th लोकेशन पे है, तीसरी 20th, ऐसा नहीं होता, इकट्ठी लिखी होती हैं. सो वो स्पेशली आसपास लोकेटेड हैं. एंड नाउ वॉट एवर इज ब्रॉट इन टू द मेन मेमोरी डिपेंड्स अपॉन स्पेशल लोकेलिटी, राइट?
Yes, ma'am.
Okay. And then definitely we want the process to be more faster. We shift a part of this page, which is a block, from the main memory to the cache as well. Okay? So that next time whenever the processor sends an address, there is no miss. It should find the respective process data or instruction from the cache itself. All right. Now we have to discuss how it is going to find now. यहाँ तक क्लियर है ना सबको?
Yes.
Okay. Now see. So we discussed that virtual memory, why it was invented. It wanted to relieve the programmers of burden of having all the everything in the main memory. So we wanted a backup which is cheaper, larger, and maybe it requires more access time, but then we can always account for the access time by having main memory and cache which are much faster than the virtual memory. So once the data and instructions are picked up from here and brought here, there is no problem, they are much faster now. So it is just a storehouse, right? And then all the virtual memory operations, everything is taken care of by what? Who takes care? The operating system.
Operating system.
Yeah, it's not the hardware, it's the operating system. Cache is taken care of by the hardware. Okay. And then it automatically manages two levels of memory hierarchy, as I just explained, so I need not explain it again. Virtual memory also simplifies loading the program for execution, called relocation. This mechanism allows the same program to run in any location in the physical memory. So this is what the diagram depicts, if you all just can see. So we have this hard disk which is having multiple processes, and now the CPU sends an address, there is a miss from here, it goes here, it picks it up from here, picks it up from here and places it here, right? And then relocation says you can pick up the data from anywhere in the hard disk and place it anywhere in the main memory. The placement policy is fully associative. We'll discuss it in detail also. Are you all getting?
Yes, ma'am.
Okay. Now, so the main operation mechanism is that there is a lot of liberty for the operating systems for relocation. It can pick up the respective instructions and data of the respective process and place it anywhere in the main memory, as depending upon its own convenience. And it is all taken care of by the OS. And then this is what I was talking about. Now this virtual memory, this can have fixed size blocks called pages, or it can have variable size blocks also. So maybe this is one, so maybe these three are one, and then these two are one, and then these two are one, and then again three are one. Such variable size sub blocks of the virtual memory are called segments. ये last time पढ़ा था. आज मैं थोड़ी सी डायग्राम्स इसलिए लाई हूँ क्योंकि मुझे लग रहा था कि आपको समझ नहीं आ रहा है. ठीक है?
Yes, ma'am.
Right. So we can have fixed size blocks in the virtual memory called as pages, or variable size blocks called segments. If it is a page, the addressing becomes very easy. See, whatever the address comes from the processor, if it is a virtual address, it just gets divided into virtual page number and then offset. But for a segment which is variable in size, every time the processor's complexity increases further, it further has to work upon how to dissociate the virtual address into a virtual page number and the offset number, virtual segment number and the offset number. So that becomes a little tough for the processor's OS to work upon. And that is why most of the times you will see that we have fixed size pages in the virtual memory. Then we were discussing that their sizes. A page size can be from 4K to approximately 64K, and a segment size is definitely variable. Depending upon the processor's convenience, it can be 1 byte, or it can be 2 raised to the power 16 bytes, or can be 2 raised to the power 32 bytes as well. तो वो डिपेंड करता है उसकी यूजेज पे, कौन सी प्रोसेस कितना स्पेस ऑक्यूपाई कर रही है, उसको पूरा एक सेगमेंट दे देते हैं। गेटिंग?
Yes, ma'am.
Yes, ma'am.
Yes. So as I was saying, page addressing has a single fixed size address divided into virtual page number and an offset within a page analogous to the cache addressing. जैसे कैश में टैग, इंडेक्स और ऑफसेट होता था, यहाँ पे VPN और ऑफसेट होता है. So this I discussed in my last class. So this is how a paging would look like. So you, whether you talk about a code or a data, the page size remains fixed. And this follows for main memory as well. So whatever is the page size in the virtual memory, it is the same in the main memory. Then only relocation is possible. See, if you have variable size pages in the main memory and a different size pages in the virtual memory, you cannot swap. It is not possible to swap, right? So the logic says that whatever the you have the page size in the main memory, that remains same in the virtual memory. And this is how segmentation look like. So a single address does not work for a segmented address. The variable size of segments requires one word for a segment number and one word for an offset within a segment for a total of 2 words of address. So addressing also becomes difficult. Segments will be variable in size. Now, since we are talking about paging as a better approach, we will discuss all the concepts with respect to paging only. Okay? Should I move ahead?
Yes, ma'am.
Yes,
Okay.
ma'am.
All right. So now if you can just see the diagram, anyone who can tell me what the diagram is depicting? थोड़ा सा. So the diagram depicts that any address that has come from the processor, depending upon the maximum memory that the processor can afford to have, it will have a maximum address size. That address is by default called as a virtual address, right? Then there is a memory map which identifies that, from the respective virtual memory to which a main memory location has the respective page been mapped. So the virtual address gets mapped to a physical address. I hope you all are getting now. Okay? Now this diagram shows you that there is an address that has come from the processor. There is a memory map which it consults, and that memory map identifies that which page number has gone to what location in the main memory. Now it does not go to the virtual memory to look for that page. If the page has been brought from the virtual memory, see, it is every time it is not the first go. Once we switch on the processor, after a first miss, the next will be a page hit, right? Okay, I have to tell you about two terms. One term is called as a page hit. And the other is called as a page fault. The way we had a cache hit and a cache miss. So what should be a page hit?
That the page, the virtual address that has been given by the CPU is found in the virtual memory.
Main memory.
Okay.
We don't want to go to virtual memory. See, it is only for the first case.
Yeah, yeah, sorry. Yeah.
Yeah, hai na?
Got that.
So yes, so for everyone else in the class, I will just say that, okay, I'll just write it over here. So there is a CPU who's sending a virtual address now, right? So it is sending a virtual address. So I'm not talking about cache anymore. We will integrate cache in the end. Okay? So there's a virtual address which has come, and definitely it goes to the main memory first. Hierarchy में पहले जो आएगा उसके पास ही जाएगा. So it goes to the main memory. If the address after translation does not match to any of the addresses in the main memory, it is a page fault. Or if the main memory is empty, if the power is just switched from off to on state, then also it will be a page fault. The way we had a cache miss. Getting everyone?
Yes, ma'am.
Yes, ma'am.
Okay. And then obviously it should go to the next hierarchical level in the memory, which is your virtual memory. So there is a page fault and it goes to the virtual memory, right? It picks up the respective frame of the page from here, places it anywhere in the physical memory because the process is fully associative. Then, if for the first case the main memory was empty, it can place it anywhere, there is no problem. What if the main memory is also full? It is going to be full, it is smaller than the virtual memory. Definitely, it will get filled up after some time. So, then some page has to be replaced. Excuse me. Excuse me. Are you getting?
Yes, ma'am.
Yeah. So this page which is replaced is based upon least recently used policy. So there is a bit also which is called as a reference bit, which keeps a track of how many times each page is accessed. The one which is least recently used is replaced. Then one more thing that has to take place is the updation of the memory map. ठीक है ना? Are you getting? जो एड्रेस फिजिकल मेमोरी के पास आएगा वो वर्चुअल एड्रेस हो ही नहीं सकता. एक virtual address, I'll give you an example. See, I have 34, 2 raised to the power 34, 2 raised to the power 34 bytes as the virtual memory size, and then 2 raised to the power 21 bytes as the physical memory size. ठीक है, कितना आ गया 2 raised to 34 कितना बना? 30 is 1 GB, 31 is 2.
16 GB.
Yeah, so this becomes 16 GB. Yeah, so 16 GB, and this becomes 4 है ना, 4 MB. 20 is 1, 21 is 2, sorry, 2 MB. ठीक है ना?
Yes, ma'am.
So our virtual memory right now is 16 GB in size, and the main memory is 2 MB in size. This is much smaller than the main virtual memory. Now, since main memory is smaller than the virtual memory, definitely it is going to get filled up after some time. है ना? 1 miss, 2 miss, 3 miss, and then it gets filled up after some time. So the address which has come from the processor, it goes to the memory map. It translates 34 bits. For 2 raised to the power 34 bytes of memory, we need 34 bits of addressing. Getting?
Yes, ma'am.
What about others? Are you all getting?
Yes,
Yes,
ma'am.
ma'am.
Okay, good. Now see, for a virtual memory which is 2 raised to the power 34 bytes in size, we need 34 bits of addressing. So the address which has come from the CPU by default is a 34-bit address. But then there is something called as memory mapping, which is done pre-hand. Beforehand, the address goes to any hierarchical level in the memory. So even before cache, this memory map happens. So this 34-bit address is translated to how much? How much? Anyone?
21.
Very good. So it is translated to a 21-bit address, and then this translation actually defines the mapping which was done earlier. Right? Getting? तो अगर ये वाला पेज उठाकर यहाँ से यहाँ लाए तो ये वाली मैपिंग यहाँ से, this means this address corresponding to what address? And definitely this is a 21-bit address and this is a 34-bit address. Though there is a logic behind this mapping, I'll tell you how it is done, but this is what it means. So this memory map identifies to the programmer, not even the programmer, to the operating system, that this 34-bit address has been translated to a specific 21-bit address, and this virtual address gets converted to a physical address before going to the cache or to the main memory. क्योंकि कैश और मेन मेमोरी को वर्चुअल एड्रेस एक्सेस नहीं कर सकता. 34 बिट एड्रेस 21 को कहां से एक्सेस करेगा? कैश तो उससे भी छोटा होगा. ठीक है?
Yes, ma'am.
Okay, good. So what I was saying was that this address which has come from the processor is a virtual address. Using a memory map, it gets translated to a physical address. The physical address goes to the cache and then to the main memory. If the respective address is found as a match, it's a page hit. And if it is not found as a match, the address goes to the virtual memory. Definitely, it wastes a few memory cycles as we discussed in memory misses. So same here, same is the case here also. And the address goes to virtual memory. In the virtual memory, definitely the address would be found. It belongs to, if it belongs to a specific process which is there in the virtual memory, it will be found. And if it is found, the page is picked up, it is placed in the main memory depending upon
The associativity, मतलब
yeah,
कौन सा?
it is fully associative by default. We don't want to waste time in, because it takes a lot of clock cycles for the access of a hard disk or a virtual memory. So the processor does not want to take that chance of missing out so many clock cycles. What it does is, it just picks the page up and places it anywhere in the main memory if it is empty. Suppose the main memory is full, then it follows. Uh-huh. Then it follows a least recently used policy, and wherever it is placed, that address is updated here. So your memory map is automatically updated. Are you all getting?
Yes, ma'am.
Yeah.
Yes, ma'am.
We have to discuss the details of how memory mapping is done and how this page hit and page fault takes place. So this was just an overview, and now we will discuss all the details one by one. Yes. So the first point that comes in the virtual memory operation is where can a block be placed in the main memory in the case of a page fault. So the miss penalty for virtual memory involves access to a rotating or a magnetic storage device and is definitely going to be very high in terms of clock cycles. Therefore, the operating systems allow blocks to be placed anywhere in the main memory, and this strategy can be labeled as fully associative. This was the case of a main memory which was empty. Then definitely, if the address is found, it's a page hit. If it is not found, it is a page fault. And well, if the main memory is full, the policy which is followed is,
Least recently used.
Least.
yeah, so we use the operating system uses the least recently used policy to replace that page from the main memory now, which is not being accessed for quite long. So which is the least recently used page. And then one more thing, there is a bit called reference bit.
Reference bit.
Yeah. So there is a bit called reference bit, which keeps a track the way we had in cache also. No, what was the bit there called?
Valid bit.
Mm-hmm. Valid bit was for something else. Here also we have a valid bit. I'll tell you later on. We had a dirty bit
30.
for write operation. We had a valid bit for read operation, and reference bit only. उसको भी reference bit ही कहते हैं for a least recently used policy. ठीक है? So just keeps a track. This is kind of a how many times the bit will be set. There will be a counter that will be counting those values. Okay, let's move on now. Okay, coming to the point that how to find a block if it is in the main memory. Now comes the address translation part, which is very, very important, and this is mainly asked in interviews. So I have many a times people consulting me before an interview, or maybe for a a written test also, कि मैम इसमें क्या होता है उसमें क्या होता है. So you should know this very well. Let's talk about it. The point is that any address, should I go back to the diagram? Okay, I can use this one. So the point is that we have fixed size pages in the main memory and in the virtual memory. दोनों फिक्स साइज पेजेस हैं, ठीक है, सेम साइज है पेज का यहाँ पर भी और यहाँ पर भी. अब suppose I have a virtual memory size of 16 GB. Let me take the same example. Just writing. Yeah. So I have a 16 GB of virtual memory and page size is, say, suppose 4 KB. How many pages are there? बताओ. How many pages are there in the virtual memory right now?
40.
क्यों 40 क्यों?
Sorry, 4 into 2 की power 10.
4 into 2. फिर से सुन लो, क्वेश्चन सुन लो. Your virtual memory size is 16 GB. You have the room size. And then a small table size, which is the page size, which has to be fit inside to the entire room. So I have to fill the entire room with tables now. And the table size is 4 kilobytes. How many pages are there?
22.
2.
2.
2 power 22.
2 to the
2
power
raised to
22. इतने ज्यादा है, आप देखो ना, मेगा में आगे 2 to the power 22. 2 to the power 22. ठीक है. Now we have 2 raised to the power 22 pages in the virtual memory. The physical memory size we took was 2 MB. 2 MB. ठीक है. And the page size remains the same. कितना है? 4 kilobyte. How many pages here?
2 power 9.
Yeah, so 2 raised to the power 21 divided by 2 raised to the power 12. Yeah, we get 2 raised to the power 9 pages. समझ आ रहा है सबको? Are you all
Yes,
getting
ma'am.
it? Yes.
Yes, ma'am.
Now, there is an address which is, I'll draw a CPU here. So, this is my CPU. Just let me know when the time is over. I still have some time. So this is my CPU and the address has come from here. So the address comes, right? And this is the virtual address. Now, there is a very important data structure in the virtual memory itself, which is called as a page table. The number of entries in this page table is equal to number of pages. ठीक है? Just like my attendance register. In my attendance register, I'll keep a record of all the students of my class. And then if I'm shifting, few students to the other section, I will mark it against their name. That XYZ students have gone to, say, section 2, section 3, for example. Getting?
Yes,
Yes,
please.
ma'am.
All right. One more thing which I want to know from you. What will be the page table size for the given case? So this data structure is called page table. I forgot to say. I said, I guess. Yeah. So we have a data structure in the virtual memory which keeps a record of all the pages which are there, their actual VP, the virtual page number, and the corresponding physical page number. Okay. So that record is maintained. So it's just a kind of a register which is like this. I'll just draw it for you. So it's just like this, and then it has two columns. One column is the VPN, the other is the PPN. So VPN is your virtual page number and corresponding PPN is your physical page number. This is how translation actually takes place. ठीक है? ये भी हम raw concept पढ़ रहे हैं, इसका refined भी आपको बताऊंगी इसके आगे. Now see, for the given case, what is the size of the page table now? What is how many entries are there? Forget about the size. How many entries are there in the page table?
2 की power
We
22.
have the number
So
of
we got 22.
Very good. So I have 2 raised to the power 22 entries in the page table. Okay. Now, with respect to those pages which are translated and brought into the physical memory, I do have a the respective ppn entry, and for those who are not translated will not have any entry. ठीक है, मतलब उनका ppn वाला पोजीशन खाली होगा, बट आपके पास टेबल में सारी एंट्रीज होंगी. ठीक है, क्लियर है?
yes, ma'am.
Yes, ma'am.
And we have specific bits which identify to us whether the physical page number in the table is correspondingly mentioned also or not mentioned also. So the way we had a valid bit there, here also we have something called as a valid bit, but I'll tell you how it takes place. यहाँ तक सबको clear है? कोई doubt है तो you can ask me. Nothing? Should I move on?
Yes, ma'am.
Okay. So we have this virtual address which has come from the processor. Before even going to the cache or the main memory or the virtual memory, it goes to this memory mapping data structure. Just now I said that it is placed in the virtual memory. Is it viable to place it in the virtual memory? If I place it in the virtual memory and my virtual memory access requires time in milliseconds, while it requires time in microseconds for the physical memory and maybe nanoseconds for the cache. Is it viable to place this table in the virtual memory?
No, ma'am.
No, obviously it is going to take a lot of time. Then what is the fun of making this table? Then what is the fun of having a physical memory? It is better to access everything from the virtual memory only. So what the operating system has done is, and what the configuration is decided is, that this page table is either kept as a smaller one in the main memory, or it is kept in a specific buffer called cache, and accordingly it is named. So it is of 2-3 types. यहाँ तक clear है तो I will move on to the next concepts. यहाँ तक clear है सबको?
Yes, ma'am.
Yes, ma'am.
Just move on to the slide. Yeah. So the both paging and segmentation, they rely on a data structure that is indexed by the page or the segment number. This data structure that contains the physical page address usually takes the form of a page table, as I just explained. Indexed by a virtual page number, the size of the table is the number of pages in the virtual address space. I should say the number of entries, because size will always be greater. There are specific extra bits which are associated with the page table also. So I should, this term rather than size should be number of entries. So the number of entries in the page table is equal to number of pages in the virtual address space. You must remember this. This is very, very important, right? For example, given a 28-bit virtual address, 4 kilobyte pages, and then 4 bytes per page table entry, the page table size would be 256 kilobytes. How did this come? Anyone who can tell me? How many pages are we having?
2 KB. 2 की power 12 pages.
2 की पावर 12. हाँ, शायद. I'm calculating. So 4 kilobytes is 2 to the power 12 again, no? 10 is 1, 11 is 2, 12 is 4, 16 आएगा. 2 की पावर 16 पेजेस हैं आपके पास. ठीक है, समझ आ रहा है बच्चे? It is very simple. It is basic mathematics. We have the total virtual memory size. We have one page size. We will divide the two. We will get the number of pages. So 2 to the power 16 are the number of pages in virtual memory now, right?
Yes, ma'am.
Now, obviously my page table will have 2 to the power 16 entries. जितने पेजेस हैं उतनी एंट्रीज बनानी पड़ेंगी. क्लास में 100 स्टूडेंट्स हैं तो मुझे 100 एंट्रीज बनानी पड़ेंगी. इट इज द सेम हियर. Every page has to be mapped to the physical memory. So if mapping has to be done, a record has to be maintained. All right?
Yes, ma'am.
Yes. So if we see further, per page, per every entry, it requires 4 bytes extra. 2 to the power 2 bytes. And this corresponds to how much? I guess 256 only. So it becomes 2 raised to the power 18. And that is 2 raised by 16 is 64. 17 is 128. Very good. बिल्कुल ठीक आ रहा. So it becomes 256 bytes as the page table size. I hope this is clear, everyone.
Yes, ma'am.
Everyone, is this clear?
Yes, ma'am.
All right. Now see, this becomes quite large. If we just see, 256 kilobytes is a big size. इतना तो कई बारी हम कैश भी ले लेते हैं. We don't want this much of such a big table size. If we keep it in the main memory, we are actually, blocking a certain space of the main memory which cannot be used for any other program or process or data. तो हम यूज नहीं कर पाए. तो फिर what we do is we place it somewhere else, and that somewhere else is cache. यहाँ तक अगर क्लियर है तो आई विल टेल यू व्हाट इज द कॉन्सेप्ट ऑफ एन इन्वर्टेड पेज टेबल and what is a translation leukocyte buffer. Clear, everyone? Should I move on?
Ma'am, time is almost done.
No, time is done. Yeah, let me see. I had time till 2:40, no? चलो यहाँ तक क्लियर है. किसी को कोई डाउट है तो यू कैन आस्क मी. At least that much you can ask me. So we have pages in the virtual memory. The page size in VM and physical memory remains the same. There is a mapping which is always done while moving pages from virtual memory to the main memory. And this mapping record has to be kept in a table which is called as a page table. This page table will have number of entries equal to the number of pages. It can be kept in virtual memory, it can be kept in main memory, it can be kept in cache. When we keep it in the cache, it is called as a translation leukocyte buffer. And when we keep it in the main memory in an inverted form, I'll tell you how next time. So that time it is called as an inverted page table. These are very, very important concepts from